welcome back. We were discussing about rectifier based voltmeters and ammeters, and just to motivate this talk once again, so we said that PMMC meters, on one hand, it is quite sensitive compared to say electrodynamic meters, particularly for low values of currents. But the problem is PMMC meter cannot measure AC, because for AC the average torque will be 0 and the pointer will not move. So, to get the benefit of high sensitivity using PMMC meter, we can actually combine PMMC meters with rectifier circuits, diodes, okay? And therefore, we can simultaneously get an instrument which can measure with high sensitivity or higher sensitivity, and it can also measure AC voltages or currents. Okay. So, in our last video we have talked about half wave rectifier based circuits, and that was actually very simple. So, today we will talk about full wave rectifier based circuits. Okay. So, full wave rectifier based circuits. Okay. So, let us recall what a full wave rectifier is. So, it is made up of 4 diodes in the form of a bridge. So, that means it has 4 arms. And it has 4 diodes in the 4 branches, and we can connect say the input between 2 opposite corners. Okay. Say this is the input, and the output of this rectifier will be between the other 2 corners of this square or rhombus, whatever you call. Okay. And we want, say, if a AC voltage is given between these 2 points, say here, so call it V in. Okay. So, we are making a voltmeter circuit, and this is the input, IN for in input, and what we will like to have is that for say positive cycle, if current flows like this, okay. So, here from left to right, then in the negative cycle we would like the current to flow say like this. Okay. So, in both the cycles we would like the current to flow here in the output, which I haven't drawn yet, from left to right only. Okay. So, this is the desired direction of the rectifier. Okay. So, do not memorize any circuit, that is my suggestion. Circuits are very logical things. You think what you want to do and you can always get that done. So, this is what I want. Okay. So, I could have drawn the circuit directly, but I am trying to motivate how to find or how to make the circuit on your own if you ever forget how it looks like. So, this is what we want. Okay. So, now, so here let me put a diode. So, I want the current to flow in this direction. So, I will put the diode like this. Similarly, here I would like to put a diode. So, let me put diodes along the direction of arrows. Okay, so I just have followed the direction where in which direction I want the current to flow, and I have put these diodes accordingly. Now, okay, now where is the meter, or where, I mean, what's there in the output? So the output of this rectifier will be connected to a DC meter, a PMMC meter maybe. So let us do that. So let's draw a PMMC meter. Okay, so I think now I can erase these arrows. So let me draw a PMMC meter like this, and like it's connected like this. Okay, so current always flows from left to right in this, through this meter, no matter whether it's the positive cycle or negative cycle. So this is the circuit. Okay, so now if I apply a voltage V in here, which is sinusoidal, here through the meter current will be always in one direction, the current will be unidirectional. So therefore the pointer can move to one side. Okay, now so this is the circuit for full wave rectifier based voltmeter. Okay, now okay, now in voltmeters, so this is the input voltage where we will connect the unknown source. So if I have an unknown source which I want to measure, so I can connect it here. So this is the source of the EMF or the voltage. Okay, okay. Now recall that when we were talking about, okay, so we can change the range by adding a series resistance. Okay, which we call the multiplier resistance. Now the question is, where should I add the add that series resistance in this circuit? Okay, so we have now the question is where to add that series resistance. Okay, we have many choices, two choices at least. So we can add it here. Okay, so this is the series resistance or multiplier resistance RS. Okay, so this is actually in series with the voltmeter circuit. So this is input voltage. So you can add it like this. You can also if you want you can also add it here. Okay, no problem. So everything is quite logical. You need not memorize any circuit. So you can add it just beside the meter. okay, because in either case this resistance is in series with this meter if you consider the path of the current. So the current flows like this. So you see that the meter and this resistance is in series, and here also if you think like this, the meter and this resistance, they are in series. Okay, so you can add it in either way. Now a small note that there will be a small voltage drop across the diodes, okay, so which is in this case it's like approximately 0.7 volt, which is the cutoff voltage for a silicon based diode, multiplied by 2 volt. Okay, so because there are two diodes in series with the meter in any circuit, even in the positive and even in the negative half of the cycle. So here these two diodes are in series with the meter, and in the other half of the cycle these two diodes are in series with the meter. So this voltage drop occurs, and for better accuracy we should consider this drop while calibrating or marking the scale of this meter. Okay, so we should consider that there is a drop. So basically the voltage that appears say across this meter and this series resistance is V in minus this 0.7 into 2, that means 1.4 volt. So we should know that there is a 1.4 volt of 4 volt drop, which we should consider for better calculations. But for most of our talk we will ignore this. At least initially we will ignore this. Okay, if time permits, later on we will see how to incorporate this drop as well in our calculation. So for most of our talk, we will ignore this drop, or that means we will assume that the diodes are ideal. Okay, so no voltage drop occurs across the diode when the current is flowing in the forward direction. So this is full wave rectifier based circuit. Now let's take a small example. Suppose we have a PMMC meter, or say let me call it a DC voltmeter. So calibrated, so this means this is calibrated for DC voltage measurement, calibrated or marked for DC measurement. Okay, we have a DC voltmeter and we want to measure say an AC voltage, AC purely sinusoidal of course. So this is the assumption we are making always. So we want to measure an AC voltage using a full wave rectifier. Now, if the meter or the pointer shows 5 volt, then what is the value of the AC voltage, unknown AC voltage? Okay. Now, when we say the value of an AC voltage, if we say not, if you do not mention anything else, it by default means the RMS value. Okay. In case of AC, by default we always mean RMS value. So the question is, what is the RMS value of the unknown AC voltage if the meter is showing 5 volt? This is a DC meter. So once again, my circuit is like this. And I'm not using any multiplier resistance since it is not mentioned. Okay, so this is the circuit. Now this is a DC voltmeter and it is showing 5 volt. So the pointer is indicating 5 volt. Now the question is, what is the value of RMS value of this voltage V in? Okay. Now, so we will ignore the diode drops. So assume ideal diode. Okay. Therefore, we know that the voltage across this meter, the average voltage across this meter is 5 volt, because DC meters like PMMC meter always indicates the average value. Okay. So the waveform across the meter, so if I call this voltage across the meter as Vm, so which is between these 2 points. Okay. So we can draw the waveform. If V in is like this, then Vm will be like this. Okay. So this is Vm, and we know the average value of this Vm, okay, is 5 volt. So average of Vm is equal to 5 volt. So this is shown by the meter. Okay. Now let's call this height as Vp peak. So this will also be same as V peak. Okay. If this has a height or an amplitude of Vp, the Vm will also have same amplitude Vp, because we are assuming the diodes to be ideal. No voltage drop occurs across this diode. So the average, so the peak voltage across the meter will be same as the peak of the input. Okay. So now the average of Vm, we can write it as V peak divided by pi by 2. Okay. If this is peak, then the average will be peak divided by pi by 2. This is what we have seen in our last video. And now this is given as 5 volt. Okay. So this implies V peak is equal to 5 pi by 2 volt. Okay. And then, so that means here also V peak is 5 pi by 2 volt, and the RMS value of V in, so RMS value of V in will be 1 over root 2 times V peak, and then it will be 5 pi by 2 root 2. okay, volt. Okay, so this will come out to be 5 multiplied by approximately pi is 3.14 and root 2 root 2 is like 2 into 1.414. Okay, so if you calculate it, so this is this will come out approximately. Do the calculation with a calculator. I do not have a calculator, so I guess this will come out to be something like this. Okay, 5.5 volt RMS. Okay, so this is the answer. Okay, now let's talk about another circuit. Okay, another full wave rectifier. This is also very similar. Full wave half bridge rectifier. Okay, the previous circuit which we have seen, okay, so this is called full wave full bridge. So this is full bridge, full wave full bridge. Okay, now the one that we are going to see is very similar. Okay, let's make it. So let's make a square, 4 arms. Say I will give the input here. Okay, and say the meter will be connected across the other 2 terminals. Okay, so this is the input. Now let's find out the direction of the current which I want, how the the direction of the current should be. So say I want in the positive cycle current should flow like this. Okay, put an arrow. Okay, and say in the negative cycle I want the current to flow like this. Again left to right through the meter. Okay, so if this is what I want, now I'll put diodes. So here I need the diode like this. Then here I need the diode upwards. Okay, but in these 2 branches I'll not put any diode, but I'll just put some resistance. Okay, so this is why it's called half bridge, because I'm using diodes only for one side of this bridge or this square structure. So I'm using diodes, half number of diodes. Instead of 4 diodes I'm using 2 diodes. Okay, but so it's called half bridge, but this is still a full wave rectifier. Because why? Let's analyze this circuit once again. So in the positive cycle, when this is positive, current will go from here, it will go like this and like this. Okay, but a part of current can also flow in this branch like this. So maybe I join them. Okay, so in the positive cycle current goes like this here, and then it has 2 paths, one like this through the meter and through the other resistance going back to the other terminal. Another path is through this other resistance. like this. Okay, so it has two paths in the positive cycle. Okay, and through the meter current is flowing from left to right, and in the negative cycle, okay, in the negative cycle current is flowing from here, it's like this, then it has two paths, one through the diode and then through the meter. Okay, let me use a different color for better visibility. So in the negative cycle, that other cycle, current is going like this, it has two paths. Through the, this is through the diode and the meter, it's going back, and it has another path which is like this, it goes directly through this resistance and back. Okay, but through the meter current is always unidirectional. So current through the meter is always from left to right. So the waveform of say or the voltage, if I call across this meter, will always be full wave rectified. So let me draw Vm, V in first, which is sinusoidal, and then let me draw Vm. Vm will be like this always. Okay, so that's why it's full wave rectifier, but it's half bridge because we are using diodes only on one half of one side of this bridge. Okay, so this is another circuit one can use just for your knowledge. And so one important fact here is that this the so say in one cycle current is flowing partly through this resistance, not, it's not going completely through the meter. Okay, so the sensitivity of this scheme will be lesser compared to the full wave rectifier, because for full wave rectifier entire current must flow through the meter. Here part of the current is bypassed through this resistance, so less current, comparatively less current flows through this meter, and this will have lesser sensitivity, but it has some other advantages in some I mean, we are not going into that detail in this course, but it has some other advantages in which we are not going to discuss now. Okay, if time permits, we will discuss it later. Thank you.